I would like to present you today a work we have been doing with friends, with Baptiste and with Fabienne, and we have been working at this project for some 10 years. We could publish last year a paper, and we are all very proud of that. The main question we asked and we discussed together with Baptiste and Fabienne is which is the impact of the rise of biocalcification and of pelagic carbonate production by coccolithophores and other nanofossils at the end of the Triassic, and how this pelagic carbonate production impacted on ocean chemistry. So maybe you know this paper, this paper by French modelers, Yves Goderis, who postulated that the rise of coccolith and nanofossil biocalcification correspond to the sharp decrease of atmospheric carbon dioxide concentration between the middle and the late Triassic. However, as you can see in this reconstruction of morphospecies richness, in the late Triassic, we only have less than 5 species of coccolithophores and less than 10 nanofossils. So it seems unlikely that there is a cause-effect relationship between these two big events. And also, what is important is that the rise of biocalcification by coccolithophores correspond also to the transition to a Neritan to a Cretan ocean mood, as defined by various modelers. And this transition is also defined as the mid-Mesozoic revolution of ocean chemistry. So this is a very simplistic model, but it permits us to understand that before the Triassic and the end Triassic, the majority of carbonate production occurred in neritic area, in shallow carbonate platforms in epicontinental seas at low latitudes. And starting with the origination of biocalcifier, planktonic biocalcifier, this production was exported towards the deep sea, the open ocean. So we have a transition from calcium carbonate only deposited on very limited areas in shallow carbonate platforms, low latitude, to a modern ocean where carbonate is everywhere, almost everywhere in the ocean, also in the deep ocean above the CCD. And this is a much more stable oceanic system with a buffering effect for exceeding CO2. But we don't know when and how exactly this transition occurred. So this is the question we had with Baptiste and Fabienne, and we tried to answer by compiling and acquiring new data on calcareous nanofossil absolute abundances and fluxes. And we used literature paper using exactly the same preparation technique we use in order to have a homogeneous data set. And as you can see, there are many areas which are not studied yet, but it's a good base to start talking about this evolution, this history of calcareous nanoplankton. About the technique, so we applied the settling method. So we prepare a slide where we have a known amount of powder, and we can count by optical microscope nanofossils and calculate a number of nanofossils per gram of rock. And we transform absolute abundances in accumulation, nanofossil accumulation rate, taking into account the sedimentation rate, which was calculated with cyclostratigraphy when possible, or using a very precise time scale, duration of ammonite zone, for instance, or other zones, using the geological time scale. And we combine this data with the dry bulk density of rock, which has been measured by Baptiste for some samples, and we have also other data coming from the ODP or the SDP volumes. So this is the main result of this work that took a very long time, some 10 years, to acquire all this data and to compile the rest of the data. And as you can see here, the nanofossil accumulation rate and the smoothing Baptiste did show that there is a very nice and very regular increase all along the Jurassic. We don't have data yet for the Triassic, but as you saw before, there are only maximum five species of coccoliths and a few species of nanoliths. So and they are very, very rare in sediment nanofossils. So we started at the base of the Jurassic. And you can see that the nanofossil accumulation rate regularly increased, and this increase goes along with an increase in species richness. Of course, these are morphospecies. We don't know the real species richness. And if nanofossil accumulation rates become stable starting from the early Cretaceous up to the Neogene, we can see that the species richness continues to increase all along the Mesozoic, and the same trend can be seen in the coccolith size. And here there is a compilation made by Marie-Pierre Aubry about measured coccoliths or data coming from the literature. Here there is average values and minima and maxima values. And here the size patterns measured by Hermann and Thierstein in SEM and optical microscope images. So we can see that both species richness and size sharply decrease at the Cretaceous Paleogene boundary, and also nanofossil accumulation rate dramatically decreased, but the recovery is very sharp, is much sharper than the very slow invasion we can observe in the Jurassic and early Cretaceous. So on the basis of all this data, Baptiste could propose three different steps in the in the history of calcareous nanoplankton. So an invasion where the accumulation rate and the species richness progressively increased. A specialization, because here we don't have an increase of nanofossil accumulation rate, but still an increase in diversification in terms of number of species and in terms of shape. The crash at the Cretaceous Paleogene boundary, and after we have a sort of establishment with more or less stable conditions. So I will focus on the invasion interval, and in particular I will focus on 5 different steps in this evolution, early evolution of calcareous nanoplankton, which are, in my opinion, very important. First of all these events are characterized by prominent negative or positive carbon isotope excursions, or by temperature changes, or by sea level changes. So all these 5 intervals are a period of major environmental changes. So now the Sinemurian Pliensbachian boundary, at the base of Pliensbachian, more or less on 190 million years, there is the most important innovation, in my opinion, for coccolithophore. Because before, in the Triassic and the base of the Jurassic, only murolith coccolith did occur. And at the base of Pliensbachian, we have this major innovation, the B-shielded coccolith, placcoliths, which can interlock each other and form a coccosphere which is perfectly locked. And the coccoliths before didn't cover perfectly the coccosphere. There are holes here. This is a Baptiste gift. So the coccosphere, we don't know fossil coccosphere of murolith, because the coccosphere was not solid. The coccosphere were rapidly disintegrated. And also the coccosphere was not continuous at the surface of the cell. And so we can retain this major innovation. And starting from there, the diversity increased much faster. So this means that this was a very successful innovation. And for the rest of the history of the group, placcoliths are dominant over muroliths. So this is a very important innovation. If we look some other organisms, just like a dinoflagellate, the Sinemurian Pliensbachian is also a period of major change, because we have the new entry in the western Tethys of some very important species which were very successful, just like this Liasidium. And maybe this species, the hypothesis is that this species was already living in the Pantalassa Ocean, and that it was migrating through the Hispanic corridor into the western Tethys. So maybe the coccolithophore followed the same path. We don't know, but now Juan and Mika are going to study Jurassic sediments from Pantalassa, from Argentina, for instance, and maybe we will be able to answer this question. Next, the early Toarcian is also a period of major changes, environmental changes, and just to show you, these changes are represented by a sharp negative carbon excursion at the Pliensbachian Toarcian boundary, followed by a second dramatic carbon isotope excursion, likely linked to volcanic activity or methane release. And in the early Toarcian, this excursion is also mirrored by anoxia, widespread in most of the oceanic sites which have been studied right now. And these two events are really different, because the Pliensbachian Toarcian boundary is a period of major diversification, as Alessandro or George have explained in their paper. And on the contrary, the excursion corresponding to the Toarcian Anoxic event it's a major crisis with the extinction. And for plankton, there are many species of nanofossil experiencing a reduction of size, a Lilliput effect, or temporarily disappearing. And this temporary disappearance This temporary disappearance is exactly the same as experienced by dinoflagellate. Dinoflagellate, as coccolithophores, have a major diversification in the upper Pliensbachian, and during the Toarcian event, they have experienced a blackout. So, two different groups have the same evolutionary response to the same paleoenvironmental event. But the most important effect of anoxia is that probably, this is an hypothesis of course, but probably promoted the colonization of open ocean, because most of the epicontinental sea were anoxic. So according to some authors, just like Malcolm Hart, it's in the aftermath of the Toarcian event that quasi-planctic forms, this means that forms which have the shape and most of the characteristic of planctic forms first occurred. And also for coccolithophores, the group, the genus of Vatsnaveria, which is the most widespread genus for the rest of the Mesozoic. So this anoxic event probably is at the origin, was the pusher of the first oceanic colonization of the open ocean. So this is also a big innovation. And concerning the Fluxes, the Fluxes in this time in the lower Toarcian are very low, very low. We are in the lower part of this scale, but the highest Fluxes are in the most proximal area in epicontinental sea of the North Thetis. So in this at that time, the ocean was still working in a neritic mode. The production was still in majority in the epicontinental areas, not in the open ocean. We also have here a region in Greece, in the Ionian Trough, which was open to the oceanic Thetis. We have a section in Tibet. We have section in Arctic, and here the Fluxes are nearly zero. So the production was in the very proximal areas. Now, a time interval which is very precious to Baptiste, the Alenian Bajocian. Here we have a big diversification of the Vatsnaveria genus. Actually, there is different morphotypes of Vatsnaveria which are replacing the Lotharingius. They are a part of the same family. And Lotharingius was really characterizing the Toarcian and Alenian assemblages. But in the Bajocian, so more or less 170 million years, Vatsnaveria took over first with the forms with the cross in the central area, with forms without structures in the central area, or the Britannica Vatsnaveria with a bridge in the central area. And these forms really dominate the rest of the Mesozoic. It's interesting to know that this change mirrored a shift towards more positive values for delta C13 and probably eutrophication of oceanic waters. And this is also attested by the widespread of the diversification and widespread of radiolarians. And in this interval, siliceous sedimentation was very widespread in many epicontinental and oceanic basins of Bajocian age. Another big innovation. The Jurassic Cretaceous boundary, of course, there is the first occurrence of Nannoconus, not only because Andre Bornemann very nicely with biometry showed that at the end of the Jurassic there was a nanofossil calcification event. So not only the big nanoliths, just like Coniosphaera, Polycostella, and Nannoconus were very abundant, but the Vatsanau area were giant, very big and very thick. So here there is a further push to carbonate production and to export of carbonate production towards the open ocean. But the most important step occurred in the lower Cretaceous, in the Valanginian, more or less 135 million years ago. And you can see here that in this area, in the Tethyan area, but also in the North Atlantic Ocean, which was opening, there is a very high value of nanofossil accumulation rate, and so both in proximal and in oceanic areas, now we have a well-established carbonate production, carbonate export to the sediment. So this is the date where we can really record a cretan ocean. This means an ocean working just like the today ocean for the first time, and it's a very young. The modern ocean is very young. Just to conclude, it took a very long time to complete this invasion phase, which started in the upper Triassic with the first occurrence of coccolithophores and other nanofossils. It took more or less 100 million years. So it's a very long invasion phase. But as we used to say in Rome and in Paris, they say the same. Rome or Paris was not done in one day. It took time. Okay, so it took time to get the modern ocean and to have this export of carbonate production to the open sea. And if you look at this curve, it closely resembles this model curve, modeling the proliferation of in culture, for instance, for algae or bacteria. So the first proliferation, exponential growth, and after the stabilization due to the carrying capacity of the environment, of the medium. And it's worth to notice that this stabilization occurred between 135 and 155 million years, in between the Valanginian and the Aptian, more or less. This means the moment where also diatoms first occurred and the moment where planktic forams explode, diversified. So probably there is a coevolution of calcareous nanoplankton and other organisms, and this coevolution created the modern ocean. I finished my presentation, so thank you for your attention. I put this image because I think that we all fall in this pot when we were young. So we were very excited with coccolithophore and with carbonates in general. And thanks to the young generation who are taking over the message. So thank you very much for your attention.